Sound wave resonates in a tube of length 2 meters with 2 open ends. What is the lowest resonating frequency of the tube if the speed of sound in air is 340 meters per second? So this is the tube that we referred to recently. I'll draw that tube. So here's the top edge of the tube. Here's the bottom edge of the tube. Try and line it up to the best of my ability for you. And we showed that the waveform within that's not drawn very well. We'll try it again. Let's just use lines. And we'll choose a different color. That's much better. This is what the wave would look like within the tube itself. And let's just make note that we have antinodes at either end and a node located centrally. If I were to select and duplicate those waveforms that are contained, we would see that one complete wavelength still corresponds with 2 times the length, and that wavelength is 4 meters as calculated previously. Since the speed of sound in air is 340 meters per second, and now we know the wavelength, computing the frequency can be done by using the wave equation. If we know the velocity and the wavelength, we can find the musical note that this will sing at, which is called the fundamental, or the lowest possible, lowest resonating frequency. Rearranging, that frequency will be the velocity of the wave divided by the wavelength. We end up with 340 meters per second divided by the wavelength, 4 meters. Meters per second over meters will leave us with 1 over seconds for units, which are unit of hertz for frequency. And then lastly, 340 meters per second divided by 4 will give us 85 hertz. Will you be able to hear this musical note that's played in this tube of this length if it's 85 hertz? The answer is yes, because it falls in the audible spectrum. Very nice. A sound wave resonates in a tube of length 6 meters with 2 open ends. What is the wavelength of the lowest resonating frequency of the tube? So if we look at the picture of this lowest resonating frequency, and we can identify what the wavelength is by looking at this, or we can apply the formula that was stated previously for closed, or rather open-end tubes. The wavelength will always be equal to 2 times the length of the tube. Now the reason that this is true is that this tube only contains a 1/2 of a wavelength. So if we were to draw the additional portion of the complete wavelength, we'll be able to see that, and let's do this in a different color. One wavelength is not contained within the tube, which is 6 meters in length, but it would take 2 times that distance for a total of 12 meters of wavelength. So the wavelength is 2 times the distance, or the length of the tube in this case, for the lowest resonating frequency. which ends up being 12 meters.